Hello and welcome to your first lesson. So good news is that we're actually going to start with a bit of review from Math 10C. We're going to start with the radicals unit. And you did cover most of what we're going to go through in this unit, but then we're just going to add a bit more. It gets a bit more difficult than it was last year. So to go over some of the terminology again. So a radical is really what you would probably recognize as like a square root, right? But now we're just also including perhaps like a cube root or a fourth root or a fifth root, that sort of thing. Okay, so those have certain names. So the square root symbol that you're used to is called a radical sign. The r in this picture is the coefficient, and that could be a number, right? That could be like 3, and it's like times this root. X is the radicand, so as a number underneath would be called the radicand. So again, if that was like, the cube root of 4, 4 would be the radicand. Okay. The index, well, that's like the cube root. So the 3 there would be the index, we'd say. All right. So for the most part, a lot of this information you'll be able to just read through, and I'm just going to mostly go through the examples kind of so you can add to your notes. So anything I don't cover, make sure that you please read through just so you have a good understanding. But I'll kind of, for the most part, stop and where I think are important things. So just looking a little bit closer at this first part, let's maybe make a note of this one. So if we had, let's say, a square root, so let's say that we were looking at the square root of 5, you don't need to write a 2, right? Like square roots are so common that we just write it like this. So there's like an implied 2 there. All right. Now, an entire radical, let's get back into these. So an entire radical would be something like this in this form, like I just showed above, where r is a coefficient, and our r value would be equal to 1. And we'd still also say it can't equal to 0, but that's implied if it's equal to 1. And what that means is you can think of there being like a 1 out front being multiplied by those. That's pretty much it, right? So an entire radical, the way you can think about that is these numbers, these radicands, are entirely underneath the radical sign. So like an entire radical. Okay. A mixed radical is kind of like what it sounds like. A mixed radical is a mix, right? You've got like a coefficient, and then you've got, some other being multiplied, right? That's beside. It's being multiplied by some other radical. Okay. Now, multiplication property of radicals. This looks kind of confusing, right? Like I want you to just be like used to this terminology or this notation. We've got x, y, which really means like x times y, right? All underneath the radical. Well, it actually works out that you can think of that as just the square root of x times the square root of y, which is kind of nice. You can just split them up. So why that's helpful, if I had like 9 times 2 underneath the radical sign, then you can split that up as the square root of 9 times the square root of 2. And then why that's nice is because the square root of 9 is actually 3. So now we simplified that, right? We turned some, term where it was like 9 times 2. We took something out, you can think of, out of the radical. Okay, now just be careful. That doesn't work for adding. If you had the square root of 9 plus 2, you can't rewrite those as the square root of 9 plus the square root of 2. So this is saying like you can't do that, right? Now, numbers that are going to be really important for you in this course are our perfect squares and our perfect cubes. You might remember this from Math 10C. So you can either write down your own list, right? Like 1 squared is 1, 2 squared is 4, 3 squared is 9. You can make your own list all the way down. We probably only need up to like 12 or 13 typically. And then with perfect cubes, same type of thing, right? 1 cubed is 1, 2 cubed is 8, and so on. You probably don't need to memorize like, some of these bigger ones, but we could be able to find, you could find it though if you needed to, right? 7 cubed in your calculator could tell you that it's 343. Okay, so maybe I'll explain why is that important. Well, looking at this list, right? If I knew, let's go to this one, right? 36. 6 squared is 36. Well, then what that means is that the square root of 36, right? Like if I just go the opposite direction is 6. So if you kind of have this list mostly memorized, which you should be able to up to 100 or up to 10 or 12 pretty easily, then you can quite easily figure out those square roots, right? Okay, so let's move on. Okay. Now, this concept is going to be something a little different. We didn't cover this much or maybe at all in your 10C course. So this one says, for even indices, the use of principal square root must be considered. Well, what's principal square root? What this means is, think about it this way. If we have the square root of 16, right? You're probably thinking, okay, I know what that is. That's 4. And you'd be correct. But I'm going to tell you right now that the square root of 16 is also negative 4. Well, why is that the case? Well, if you think about it, you're going the opposite direction, right? Like if I go 4 from this first one, 4 squared is equal to 16. Yeah, that's why the square root of 16 is 4, positive 4. That makes sense. But look at it this way. If I went negative 4 in brackets squared, well, that's also equal to positive 16. So if you go backwards, right, from 16, the square root of 16 is 4. It's also negative 4. So it actually works out every time you take the square root of a number, you always should be thinking there's a positive and a negative version. Well, the positive version is just more common. We just kind of use it more often. We call it the principal square root. The negative version would be called like the secondary square root. And like, I guess you might be saying, like, how will I know whether it's negative or positive version? Really, if the question doesn't say anything, like if it doesn't really give any context for it, then it would just be the positive square root. In this course, it would typically be the positive square root, but there will be cases moving forward, later on, maybe in this course or in 30-2. So one more thing to consider here with even indices, when we have to consider the principal square root, is we also have to think about this, that is there ever going to be a case where you can take the square root of, like, let's say negative 16, right? Would that ever work? Not really, right? Because that would be, okay, well, 4 squared is equal to 16, or is equal to positive 16. And like we said, negative 4 squared is equal to positive 16. So taking the square root, like going the other way, that would never happen, right? So you're never going to have a negative under a square root. Now, if we look at odd indices, it actually can be the case. You can have a negative underneath, right? For, like, let's say cube root of 8 and the negative, or cube root of negative 8. In this case, we've got the cube root of negative 8. Well, you can think of what that is. Let's go the other way. So the cube root of 8 is equal to 2, because 2 cubed is equal to 8, right? 2 times 2 times 2 is equal to 8. Now, if you look at the cube root of negative 8, well, that's equal to negative 2. And think of it this way, right? Because it's like negative 2 cubed is equal to 8, or sorry, negative 8. And yeah, why is that the case? It's all because this one's odd, because that's really saying like negative 2 times negative 2 times negative 2 is equal to negative 8. And that makes sense, right? Because it's like a negative times a negative is a positive, and then that positive times a negative is negative. That's only going to happen when we have an odd index. So 3, 5, 7, 9, and so on, right? Okay, so now let's look into converting. This is a really important skill for this course. Converting into mixed radicals. So we're going to take an entire radical and we're going to convert it into a mixed radical. All right, so I have the steps above, so feel free to look through them, but I'm just going to kind of go through some questions and we'll just do this one by one. Okay, so the square root of 45. What can we do here? Well, we are going to rewrite the square root of 45 as, and I want to write it as some perfect square times some other number. So what I like to do is make a list of my perfect squares just somewhere else on my page. So, 1 times 1 is 1, 2 times 2 is 4, 2 squared is 4, 3 squared is 9, 4 squared is 16, 25, 36, 49, 64, 81, and we're probably good with 100. Just we'll go up to that, right? So why are those nice? Is because I know the square root of all those numbers, right? So what I'm going to do is I'm going to try to rewrite 45 as one of these numbers times something else. Okay, so maybe you can figure that one out. The square root, or 45 could be rewritten as 9 times 5. Well, why was that helpful? If you remember above, we can rewrite that now as the square root of 9 times the square root of 5. Why is that helpful? Was because now that I have this just square root of 9 sitting out in its own, the square root of 9 is really just 3. So this is really the same thing as 3 root 5. That's it. Okay, moving on to the next one. So let's try this. So 75. So 75, if I look through my list, you know, if you can't think of it either, this one's fairly straightforward, but if you can't think of the number, right? Well, what you could do is you could go 75 divided by one of these numbers and see if it goes into it, just with your calculator, right? If you ever get stuck. So in this case, if I go 75 divided by 25, I get 3. So 25 is my number here. So let's rewrite this guy as the square root of 25 times 3. Okay. Now, in the last case, you can do it both ways. You can think of it both ways, right? I split this up as the square root of 9 times square root of 5. I could do that again, but at this point, what I kind of like to think of it as is, like, I can skip that step, right? I'm like, okay, I got the square root of 25 trapped under the square root here. Well, I get to take that guy out because I know the square root of 25. The square root of 25 is 5. So that guy just gets to come out as a 5. And then that 3 is still just trapped in there. So I still have the square root of 3 left over. And that's it. Okay, let's try some more. So this, there's a negative sitting out front, and then we have the square root of 432. Okay, so for this one, I wrote down my perfect squares again. Turns out we actually need to go up to 12 squared. Is 144, right? And so we'll go 132, and this is one of the ones where it's just not so obvious, what goes into it, right? Like maybe you can figure it out, but maybe not. Maybe I think 64 goes in. So maybe I'm like, okay, 432, and I want to see if 64 goes into it. So divided by 64, right? And I get 6.75. Okay, so I can't go 64 times something to get 32, right? Like some other number, whole number. Okay, so that's not it. And you can keep trying some other ones. Turns out it's 144. And what you should do when you're doing these, by the way, try for the bigger number, right? Like it'll work, like sometimes multiple numbers would go in, but then it'll just take 2 steps. You'll have to do it again when you're done. I'll show you an example of that, hopefully the next ones here. But 144 goes in, so just to show you that it does, you go 132 divided by 144, and it goes in 3 times. Okay, so 3 times 144 is 132. So let's rewrite this as the square root of, and we're going to write this as 144 times 3. All right, so now 144 is a perfect square. I know the square root of that. The square root of 144 is 12, so I get to take that guy out as 12. Okay, so it comes out. Now, the new thing here is this negative is sitting out front. It's just out there, right? This is like -1, you can think of it as. So it's like -1 times the 12 I'm bringing out. This is just -12 now. And then this 3 is still just trapped in there. So I still have root 3. Okay. All right, let's look at the next one. Now, we've got the cube root of -32. So first off, are we allowed to have a negative under the radical? Or like for like our radicand? And the answer is yes, because this is odd, right? If it was even, if it was like 2 or if it was 4 or 6, this wouldn't even exist, right? But because it's odd, you're allowed to do that, right? The answer is just going to be -2. Okay, so now 32. So you might be thinking, perfect, 16, right? 16 goes in. But the problem here is that we can't use this list anymore, right? Because this was our list of perfect squares. We need a new list. We need our list to be perfect cubes. So like 1 cubed is 1. 2 cubed is 8. And then 3 cubed is 27. and so on, right? So that's my list. So I think we're good because, it's not going to be 27. It's definitely going to be 8 in this case, right? So let's rewrite this. This would be the same thing as the cube root of, you'll say this is negative 8. I'm just, again, leaving the negative right there. Just negative 8 times 4. All right, so now we get to take the 8 out, right? So I get to take that 8, I get to move it out. And when you think of it, it's the cube root of 8, right? So I get to take that out as a 2. And you could do that, right? Like, I'll just show that. This would be the same thing as like 2 times the cube root, and then like think of that negative as staying in there as negative 4, right? But I don't really want to leave the negative in there. So what I'm going to do, I'm actually going to take that negative out with it, because the cube root of negative 8 is negative 2. So I just got to like bring it out with it. And then we've got left inside there, still got the cube root of, and then that 4 is trapped. It's still in there, right? Because we don't know the cube root of 4. We know the square root of 4. We don't know the cube root of 4. So it has to stay. All right, square root of 98. Okay, so I made myself a little list here. I'm only going to go up to this because I don't think I'm going to need any higher based on the numbers I'm looking at here. So the square root of 98. So it might not be so obvious right out of the gates. It's probably not going to be 64, right? Because like 64 times 2 is already too big. So it's not going to be that one. And let's just try like the next one. So 98, let's try dividing by 49. And it does, right? So that one works. So it's just 49 times 2. All right, easy enough. So the square root of 49 times 2 is the same thing as 98. I know the square root of 49 is really 7, so that just gets to come out as a 7. So I have 7, and then the 2 still trapped in there. All right, looking at this one. Now we've just got the 2 out front as our coefficient. So we'll just handle the 50 first. So I can rewrite 50 as, probably this one, 25 times 2. I know the square root of 25. The square root of 25 is 5, right? Because 5 squared is 25. So think of it as coming out. And this is what happens. It's like the 2 still out there. And then you're going to bring that 25 out. So now that's a 5. And the 2 and the 5 are sitting beside each other. That means they're being multiplied by each other. And then that 2 is still trapped. So 2 times 5 is 10. So this is 10 root 2. You'll get good at that. You'll go like, okay, square root of 25 is 5. You'll bring it out and be like, okay, multiply by the 2 is 10. Like you'll get to the point. You can just do that in one step. All right, next one. The cube root of 16. All right, so I need my list of perfect cubes. Probably not very many. 1 cubed is 1. 2 cubed is 8. That's probably the one. That's probably just 8. All right, so cube root is going to be 8 times 2, right? 8 times 2 is 16. That 8 doesn't need to be in there anymore. I get to bring it out as a 2. So I still have 2, and then times the cube root of, and then that 2 still trapped. All right, so for the next one here, I made my list of perfect squares again because I'm dealing with a square root. And this negative 3 is just hanging out front. Okay, so 162. I want to find numbers that goes into. So, all right, so we'll go 162. I think 9 goes into it, right? So let's go divided by 9. And it does. Okay, so 9 times 18. So we get negative 3 times 9 times 18. And that works out, right? So I'm going to bring this 3 out, or this 9 out as a 3, right? Because the square root of 9 is 3. You might be able to do this in your head too, right? Now we've got like negative 3 times the 3 we're bringing out. So negative 3 times 3, this is negative 9. And then my square root of 18 is still trapped in there. Okay, but now there's a problem here, right? I can actually take out more. The square root of 18, right? Like I can rewrite 18 as 9 times 2. So this would be the same thing as negative 9 times 2. Okay, so then I can bring that 9 again out as a 3. So 9 times 3, this is the same as negative 27, and then root 2. Okay, so there was 2 steps there, right, which was a little bit annoying. Now, this is what I was saying before, is why I think we should probably actually just see if anything larger goes in first. Right off the bat there, we could have went 162 divided by, and 81 goes in, right? 81 times 2. So watch this. This would have been a lot easier. We would have had, just from the beginning here, negative 3 times 81 times 2. 81 gets to come out as a 9, right? Square root of 81 is 9, so that comes out. Negative 3 times 9 is negative 27, and then you still got that 2, so root 2. So wasn't that easier? So just a little, I did it both ways because I wanted to show you that it's kind of nice to get the larger number first, because if you do the smaller number, it might take multiple steps to get your answer. All right, so now the last one, that really was like the main skill in this this unit. We're going to go the other way now. We're going to go from a mixed radical back to an entire radical. This one's actually a little bit easier, but it's a little less common. You don't usually want, there's not usually a need to go this direction. The one need you might have is just when it's written as an entire radical, like, the square root of 75 or the square root of 76, It's easier when it's in this form to see which of those numbers is bigger without a calculator, right? That's one of the reasons you do this, but typically you go the other way. You'd simplify, you go the other direction. But, okay, this one's actually easier to do, because now what we're going to do is we're going to take this 5 in this one, and we are going to try to put it back in. We want it entirely under the radical, right? Well, if you think about it, the way we were taking these things out in the last step is we take the square root to bring them out. Okay, so if I want to put it back in, I need to square it. So this would just be the same thing as the square root of, and then think of this as like the 5 going back in as 5 squared times 7, right? Because it's just beside the 7 now. So this is like 25 times 7. So I'll write that 25 times 7. And then we actually just multiply those, right? So this would be the square root of 175. And then leave it just like that. That's an entire radical. Okay. Now the other way, with a cube root now. So 3, I want to put it back in. So this would be the same thing as the cube root of. And if I'm putting it back in, right, I would cube root it to bring it out. So I need to cube it to put it back in. So this is 3 cubed times the 4 that's in there. Okay, so this is really like, not 9, sorry, 3 cubed. So 3 times 3 times 3 is 27 times 4. So this is the cube root of 108. Yeah. Okay. So quickly look at these ones. So 8 squared, so we'll bring back in. So we get 8 squared times 5. So this is like 64 times 5. And you know what? To make things easier, I'm just going to grab my calculator. 64 times 5, so 320. So this is the square root of 320. Okay. All right, so let's put this negative 2 back in. So this is now the cube root of. So we're going to think of it this way as like negative 2 cubed, right, like that, times the 5. So 2 cubed is 8, right? 2 times 2 times 2 is 8. Negative 2 cubed is negative 8. You might have an alarm bell ringing being like, can you have a negative under there? And the answer is yes, because it's an odd index, right? So negative 8 times 5. So this is the same thing as negative 40. All right, let's do it again. So we've got, negative 2 squared, bringing it back in. So this would be the same thing as, so negative 2 squared times the 18 that's in there. So now what is negative 2 squared? Well, that's positive 4, right? When you have an even power. So this would be the same thing as 4 times 18. So this would be the same thing as the square root of 72. Now you might be thinking, how would I ever get like a negative? Because this was negative, right? Like, and this one's not negative. How would I ever get a negative back out? Well, remember that principal root thing, right? Whenever you take the square root of a negative, or whenever you take the square root, rather, you get a positive and a negative version. So we were just looking at the negative version there. Yeah. All right, next one. So 1/2 times the square root of 10. So we want to put that back in. All right, so let's rewrite this. So this would be like 1/2 squared inside there times 10. Now, this might be a little bit scary. I'll just write it over here a little bigger for you. 1/2 squared. When you square a fraction like that, all you do is you square the numerator and you square the denominator. 1 squared is 1. 2 squared is 4. So this is really the square root of 1/4 times 10. Okay. Now, 1/4 times 10. Multiplying is the easy one with fractions because you can think of it like this, right? Again, I'll just write it a little bigger. It's like you've got 1/4 times 10, and think of it as like 10/1. So now multiplying is just straight across. You've got 1 times 10 is 10. 1 times 4 is 4. So you've got like 10/4. And you can simplify that, right? Those are both even numbers. So divide the top by 2, the bottom by 2. This is 5/2. So this would be the same thing as the square root of 5/2. All right, so now we're going to throw in, you probably weren't expecting this, Pythagorean theorem. And the reason for it is because Pythagorean theorem has squareds in it, right? So when we solve for things, we might need to use a square root. So let's see how this goes. So if you remember with Pythagorean theorem, it's a squared plus b squared is equal to c squared, like we see here. And a and b, if you remember, don't matter which side's which, right? Like you could swap the a and the b, but the c always has to be the hypotenuse in that equation. So let's look at this one. So it says solve for x. All right, so x here is really the hypotenuse. So what we can say is x squared is equal to 6 squared plus 8 squared, right? Because really that was c squared is equal to a squared plus b squared. That's all I did there, right? All right, so let's put that together. So we've got x squared is equal to, and at this point, yeah, so we got 36 plus 64. So x squared is equal to 100. Okay, so does that mean this is 100? You can probably tell that that's wrong right at the bat, right? If that's 6 and 8, that's definitely not 100. Last thing we had to do there, if you want to get rid of the squared in this, because I don't want x squared, I just want x, is we need to take the square root of both sides. So the square root of x squared, right? This, you can think of like the square root and the squared just canceling. So I've just got x is equal to, and then the square root of 100, well, that's a perfect square. That's just 10. There you go. X is equal to 10. All right, let's look at the next one. Solve for y. All right, so in this case now, so it's, a squared plus b squared is equal to c squared. But this time we have c. The 12 is our c, right? And we're looking for, and again, it doesn't matter which one we call a or b here, right? What's going to change is if you were to solve for like a squared here, right? You can think of like, well, if I wanted to get a squared on its own, you'd subtract b squared from both sides. So minus b squared. So it's like we have a new equation. It's like a squared is equal to c squared minus b squared, right? And that'll be the case. It'll be a subtraction when you have the hypotenuse. Okay, so if we're solving for y, instead of using an a, I'll use a y. So I'll say y squared is equal to, this is the hypotenuse, so 12 squared minus 8 squared So we've got y squared is equal to 144 minus 64. So y squared is equal to 80. All right, so now that's what y squared is. So to find just y, right, we'll take the square root, right, because we'll take the square root of both sides there. So the square root of 80. Now, at this point, what you would have always done since grade 9 is you would have just thrown that in your calculator. Let's do that. You would have went, okay, the square root of 80 is that, right? This decimal. Now that's true, right? But this is one of those numbers like pi. It's an irrational number that just goes on forever and never repeats, right? So at some point you'd have to round that. Maybe you call that 8.9, maybe you call that 8.94 or whatever it is, right? But in that case, if that was our solution, you'd say this. You'd say y is, and then you can use like little squiggly lines and say y is approximately equal to, and then whatever that was. Gotta find a better way to go back to it. 8.9, right? It's approximately equal to 8.9. I say approximately because the exact answer is irrational and never ends, right? In math, we like to be very accurate. So what we're going to do is instead of writing it as a decimal like that, is we're going to keep the square root because this will be like an infinitely accurate answer. So you'd actually just leave your answer like this. Like that is a number, the square root of 80. But what we want to do though first is we want to simplify as much as we can. We want to take out as much as possible, right? Okay, this is right, but it's just not the right, as good a form or as simplified as it could be. So we'd say y is equal to, and then 80. All right, so 80 can be rewritten as 16 times 5. And I know the square root of 16 is 4. So that gets to come out as a 4. So y is equal to 4 times root 5. And now this is kind of weird for students. That is my answer, right? Like you actually just type that in. Like 4 root 5 is the solution there, which is the same as this. That is that number. It's just infinitely accurate. This includes the infinite number of decimals that are in this irrational number. Okay, last one. All right, so Steve is turning half of his backyard into a chicken pen. His backyard is, well, that's definitely a typo. I'm hoping it should be correct in yours, but this should say 24. And this should say 45. For some reason, they got tripled. All right, so that's the best. That would be a very big backyard. So that's the rectangle of his backyard. He wants to put a chicken wire fence that stretches diagonally from one corner to the opposite corner. How many meters of fencing will Steve need? Okay, so let's try a little sketch. So he's got a rectangular backyard, and it's 24 by 45. And he wants to put chicken wire fence that stretches diagonally from one corner to the other. So that'd be like from this corner up to this corner. Maybe you see where we're going with this, right? We just made a right angle triangle, so we can use that. All right, so where is his chicken wire fence? So it's just half of his yard, right? So he's only going to do it including the hypotenuse there. And then he'll need to, he's going to want to make his triangle like the blue one here. Okay, so we really just have a right angle triangle. So I have the 24 on that side. Maybe I'll just bring it back over to this side because it'll be the same thing. And we need to figure out this length, right? So this would be like our C. I'll call it X. Okay, so we're going to say X squared is equal to, and this is the hypotenuse, so it's going to be 24 squared plus 45 squared. So X squared is equal to, and with numbers like this, I'm definitely just going to throw out my calculator. So 24 squared plus 45. Oh, I didn't call that squared, did I? Okay, 45 squared equals. Okay, so we get 2,601. Ooh, and I'll correct that to the power of 5, whenever I did that. Okay. All right, so now last step here, we're just going to go, okay, we'll square root both sides, right? So x is equal to the square root of 2,601. And now from here, well, we could rewrite this as a mixed radical as much as we could, right? Or leave it like this. This would be like an exact way to leave your answer. But really, in this case, we want to know, because it's fencing. This is like a real world thing. I just want to actually figure out what that number is. So we would just put that in our calculator. Right? So, because I just want to know approximately, really, because it's going to be very close. So I'll say the square root of. You can either write that number again in TI-84 or go second answer. And grab the number from above. Okay, so actually this one was a perfect square anyway, so this one worked out. So x is equal to 51. Okay, so this was 51. Now if we assume that these two sides weren't already fenced, then we'd need to fence all of it, right? So then we just add it all together. So we just say the total fencing here would be 51 plus the other side, 24 plus 45. So this would be 120 meters of fencing. And then you'd circle your answer if you were writing this out so your instructor knew what you thought your answer was in this.